Hi, I'm Alex. Hopefully you know that already. So far this semester we've been talking a lot about very broad concepts about what makes our planet what it is and where our planet came from. Things like the universe, the formation of the universe, the formation of our solar system, all that stuff. Well, what I wanted to talk about today was the matter that composes our planet. And specifically, we're going to talk a lot about minerals today. Minerals are actually the building blocks of all the solid material on our planet, but not everything is a mineral. So what makes a mineral a mineral? Well, minerals have a very specific definition, and I'll get to that in a second, but why do we study minerals in the first place? We study minerals because they provide a lot of resources. They provide a lot of our resources for jewelry, for pottery, building materials, metals, things like that. Minerals also tell us a story about what happens inside the planet. Some minerals form at different temperatures, some minerals form at different pressures. So when we find specific minerals, they tell us exactly how that mineral formed and where it was and what conditions it formed under. So it gives us a little bit of a window, a little bit of insight into what makes our planet tick. So what is a mineral? Well, a mineral actually has a very specific definition. If you're following along in the PowerPoint lecture, there are some bullet points right there. A mineral has a specific definition. The definition that I was trained in, and the definition that you're going to learn, is a mineral is a naturally occurring, inorganic, crystalline solid with a fixed or limited range in chemistry. And that is verbatim how my professors taught me, how I understand a mineral, and how you're going to learn it. So that is actually what a mineral is. Now, when I say naturally occurring, that means it has to occur in nature, meaning we can't make it, we can't synthesize it. So cubic zirconia, some of you might have one of those on your rings and be a little mad at your boyfriend now. A cubic zirconia is not a mineral. It's synthetically made. Synthetic rubies that you use on your watch face, things like the sapphire watch faces that you might have, those are synthetic. They're not technically a mineral. So minerals are also inorganic, which means that they cannot contain organic compounds. So take sugar, for example. Sugar is a crystalline solid, right? It looks kind of like a mineral, grows kind of like a mineral, but it's not a mineral. It's actually composed of glucose. It's actually an organic material. So it's not an inorganic material. It's not a mineral. Minerals are also crystalline, meaning that minerals have a basically indefinite, regularly repeating structure. All the molecules that compose a mineral, they are actually put together in a very repetitious pattern. And you can repeat this pattern to infinity. You can have a mineral as big as your house, you can have a mineral as small as your pinky nail. So minerals have a crystalline structure. Now, there are certain things that may look like minerals that are not minerals. One example of that would be glass. Now, I'm sure many of you have heard that glass is not a solid, right? That it's a very slow-moving liquid. Anybody? Show of hands? Yeah, you in the back. So it's not actually a slow-moving liquid. Glass is actually solid, but it's what we call an amorphous solid. Now, if any of you have sat down with your grandmother, like I have, and made a jigsaw puzzle, you've probably started putting together the jigsaw puzzle and found like a few corner pieces, found a few pieces over here, and a few pieces over there. You put them together, you have a few pieces, but most of the jigsaw puzzle is still in those little individual pieces. That's what an amorphous solid is. That's what glass is. Glass is composed of silica tetrahedra, which I'll talk about in a little bit, but those little bits and pieces of minerals are kind of floating around in this massive matrix of individual molecules, and that's what makes glass an amorphous solid. That's why it breaks the way it does. That's why it has all the properties it does. It's not a crystal. So glass is not a mineral. So we've already covered that a mineral has to be solid. That's pretty self-explanatory. A mineral also has a defined but slightly variable chemistry. This slightly variable chemistry allows it to have different forms, but maintain the same characteristics that make it a specific mineral species. So you might have quartz, for example. Quartz is composed of silica dioxide, so silica and two oxygens. That's where we get our silica tetrahedron. Now, within that silica tetrahedron, we have a very small silica atom and 4 very big oxygen atoms surrounding it. Now, because of the size of those minerals, only certain things can fit in. This is a silica tetrahedron. It has a silica with 4 oxygen atoms surrounding it. Because of the nature of this structure, only certain things can fit in that spot. The idea here would be like taking this Dixie cup and putting a ping pong ball inside it. That ping pong ball fits pretty nicely in that Dixie cup. Now, if I take some other ball, like this tennis ball, and try and fit it into the Dixie cup, it doesn't fit very well. A mineral is very much the same. You have certain spaces where certain molecules can fit, certain atoms can fit. And if they don't fit, then they can't be part of that mineral. So it can vary a little bit depending on what size atoms are compatible, but for the most part, that mineral has a fixed chemistry. So those are the defining characteristics of a mineral. So if I were to ask you on any sort of upcoming quizzes or tests that you might have, I don't know, say next week, if I were to ask you what the defining characteristics of a mineral were, you would say they are naturally occurring, inorganic, crystalline solids with a fixed or limited range in chemistry. What is a mineral composed of? A mineral is composed of one or more elements, things like copper, zinc, iron, nickel, etc. Those are naturally occurring elements. Those are singular atoms with a single number of protons. The number of protons defines defines what species of atom that is. But each of those atoms is composed of subatomic particles. And there are various updated models of atoms. We're going to go with the somewhat archaic Bohr's model of an atom. Atoms are composed of protons, neutrons, and electrons. Protons are positively charged, neutrons have no charge, and electrons are negatively charged. In an atom, at the center, you have a nucleus that's composed of several protons and several neutrons. Surrounding that nucleus, you have orbiting an electron, or multiple electrons. If you have 2 protons, then you'll have 2 electrons to balance them out. So, a neutron walks into a bar. He has a few drinks and decides to leave. He says, "All right, bartender, what do I owe you?" Bartender looks at him, he says, "For you, no charge." So, an atom is composed of those 3 particles. Protons define what that atom is, what element that atom is. Now, if you have an uncharged atom, the number of protons has to be balanced by the number of number of electrons. So, if you have 2 protons in an atom, that means you have to have 2 electrons circling that atom to balance out that charge. Now, if you have 3 protons in an atom, you have to have 3 electrons to balance out that charge. Now, the neutrons are hanging out in the nucleus of an atom as well. The neutrons sort of act as a buffer. They sort of act like glue for those protons. Those protons don't want to be hanging around together, so the neutrons kind of help facilitate that. And the electrons are orbiting this nucleus. So you have a central nucleus, and you have a bunch of electrons orbiting. You have protons and neutrons in the center. Surrounding these are electrons. These electrons occupy a shell around the center of that atom. The protons are balanced by those electrons, and this shell wants to be full. This outermost shell is called the valence shell. Now, this first valence shell, if you have 2 protons, you will have 2 electrons. That valence shell is full. If I had an extra proton, or even 2 more protons, I'd have to balance them by adding another shell. Because this shell is full, I have to go to the next energy level. This shell has enough room for 8 electrons. Once it reaches 8 electrons, this shell is full. Every successive shell after that builds on top of that. Atoms are like onions. They come in layers. Or, I don't know, what about parfait? Everybody loves parfait. Who the hell you say, let's go get some parfait, and they be like, oh, no, hell no, I don't like no damn parfait. They continuously grow on top of that based on their energy level, which means you have a bunch of successive shells of electrons. Now, the outermost shell is the only one of those shells that actually does any interacting with the stuff around it. That's what we call a valence shell. A valence shell is an important shell because the valence shell is what actually interacts with everything that surrounds it. So if those electrons in that valence shell want to interact with other stuff, it's going to react. Now, that's important because those valence shells really like to be full of electrons. Valence shells contain a total of 8 electrons, which means if that valence shell is full, then it will have 8 electrons in it. If that valence shell is not full, obviously it's going to have less. So, some valence shells contain 1 electron. Now, the question here is, if that valence shell really wants to be full, the outermost shell really wants to be full, you can get to a full state, a full valence shell, by either dropping 1 electron or picking 7 electrons up if that valence shell has 1 electron in it. So, what's easier for that atom to do? Is it easier for it to drop 1 electron to reach the next valence shell down, which is full? Or is it easier to add 7 electrons onto it to get to a full state? In this atom, we have 4 protons in the nucleus. This shell is full. It has 2 electrons. The valence shell, the outermost shell, has 2 other electrons. This atom is balanced. However, there are several empty spaces in that outermost shell. That means that this valence shell wants to lose 2 electrons. So that atom really wants to drop 1 electron, to get rid of 1 electron out of its valence shell. Now, what happens when it gets rid of an electron? Well, you don't have a balanced charge because the number of protons in the nucleus no longer equals the number of electrons that are orbiting it. So, because you've gotten rid of an electron, you now have a positively charged atom. All the protons, they have positive charges, remember? So, you have a positively charged atom. You've gotten rid of 1 electron. You now have a full valence shell. That atom would be happy. Now, you can also go the other direction. There are some atoms that have 7 electrons in their valence shell, and those atoms would really love to pick up an electron. So those atoms pick up an electron. They now have a full valence shell. They have 8 electrons in their valence shell. Now, they've picked up another electron, so if they have more electrons than protons, what charge would they have? They'd be negatively charged. So you have a negatively charged ion. That's what we call an ion. When it picks up or gets rid of an electron and contains some sort of charge, that is an ion. So we have these valence shells that really like being full. And they really like interacting with other stuff around them, which means they start bonding with other atoms to form molecules. When they bond with other atoms, that means that their valence electrons are interacting all the time. They're doing one of several things. They're either sharing these electrons, they're borrowing these electrons, or they're passing them around. And we're going to talk about that here in a second. There are several types of bonds. One of those is what we call an ionic bond. An ionic bond, which you can't see because the screen is way too bright, this is what happens when you share an electron, or when you borrow an electron. These 2 atoms have valence shells that aren't full. Here's the nucleus, here's some electrons, here's a nucleus, here's some electrons. This valence shell only has 1 electron in it, meaning that it has 7 other spots for electrons. To get to the next valence shell that's full, this one, it would have to lose this electron. So, sodium wants to give up one of its electrons. Chlorine, however, has a nucleus surrounded by several electrons, and to get to a full valence shell, it wants to take an electron on, because it wants to fill this empty spot right here. It has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. It wants to fill this spot, meaning that sodium wants to give one of its electrons to chlorine. So chlorine takes its electron, fills its valence shell. Now sodium is short 1 electron, chlorine has an extra electron. Sodium becomes positively charged because it has too many protons. Chlorine becomes negatively charged because it has too many electrons. Sodium wants to get rid of its electron, chlorine wants to take on another electron, so they decide to share. Sodium gives its electron to chlorine, and now all of a sudden we have two ions. Sodium is now positively charged, chlorine is now negatively charged, and when you have two atoms that are oppositely charged, they want to attract. So, sodium and chlorine attract together, they bond, they form an ionic bond. Two ions bonded together. That forms sodium chloride, and that's what you use at your table. That's what you put on your popcorn, put on your French fries, table salt. All right. So that's an ionic bond. Now, the next bond that we're going to talk about is covalent bonds. And just like the name might imply, you're actually cooperating. Your valence shells are cooperating. You have a covalent bond. And this is what happens when you have something like carbon. Carbon has 4 electrons in its valence shell. So it's just as easy for it to get rid of electrons as it is to take on electrons, so it doesn't really know which way to go. So what it does is it shares its electrons with its surrounding neighbors. So its valence electrons are shared between its neighbors, and because they're all sharing these electrons together, they fill up their valence shells and they bond together. So they're sharing electrons and they form a covalent bond. Now, the third type that we're going to talk about, which we're not going to go into too much detail, is what we call metallic bonding. Metallic bonding is very specific to metals. And you might have experienced this if you've ever touched an electric fence. Metals allow electrons to move and flow. Metals allow electrons to flow freely between the atoms, which means metals are malleable, they're ductile, they can be pulled into wires, they conduct electricity. That's what this metallic bonding is, what gives metal its very specific properties. And then there's one other type of bonding that we're going to talk about. It's not necessarily a type of bonding per se, but it is an attractive force. This is what's called van der Waals force. Now, van der Waals force is a slight attraction to molecules that are polar. Now, what is a polar molecule? A polar molecule is one whose shape allows it to have a certain gradient of charge, which means on one end of that molecule is positive, has a positive charge, the other end of that molecule has a negative charge. So overall, that molecule acts kind of like a bar magnet. So one positive, one negative end, and if you get another one of those molecules near it, the positive and negative ends are going to line up. So those molecules are going to be weakly attracted to one another. You might have actually experienced this if you've looked at water bead up on your windshield or something like that. Example of a polar atom. Water molecules look like this, kind of like Mickey Mouse ears. Oxygen with 2 hydrogens attached. Now, because those hydrogens are all up here sharing electrons, that means that all your electrons are concentrated in this area, which means this side has a negative charge. Meanwhile, this side has a positive charge. If we have several of these molecules lined up, the positive end of one atom is going to be attracted to the negative end of another. This is what we call van der Waals forces. Each of these atoms or molecules is attracted to one another, which holds them together. Van der Waals forces are what give water its surface tension. This is what we call cohesion. And this is all because of van der Waals forces. Now, it's not limited to water molecules. That's just a good example. But van der Waals forces are what holds some minerals together. It's a very weak bond, and it's easy to overcome just by yanking that mineral apart. So those tend to be very breakable minerals. But van der Waals forces are an attractive force. So, 4 attractive forces: ionic bond, covalent bond, metallic bond, van der Waals forces. Now, if we were to try and break these bonds, the question is, what would be easily broken? Well, if I'm one molecule, one sodium molecule, and I share my electron with chlorine, well, we're not actually touching. We're just kind of holding on to each other's molecules. It's kind of like you give a guy your camera to take a picture, and suddenly that guy with your camera runs off, and you never see him again. All right, maybe that's a negative example, but the idea is that we're saying you have two atoms that are borrowing electrons. One is loaning its electron to the other, which means that they're not actually touching, and you can actually pull those atoms together or apart pretty easily. Sodium and chlorine atoms are held together by ionic bonds here. And because water molecules are so polar, they can actually pull them apart. If they work together and they attack these sodium atoms, then these water molecules can actually rip apart the sodium and chlorine atoms and dissolve them. Now, a covalent bond is a little bit different. In covalent bond, they're sharing their electrons, which means each atom is directly contacting the other atom, which means they're gripping each other pretty tight. They're all holding on to those electrons because they all want those electrons. So you try and pull those atoms apart, and it's a lot harder than it is to pull ionic bonds apart. And you can see this if you try and dissolve something in water. Salt, for example, sodium chloride, it's an ionic bond. It dissolves really readily in water. Other minerals don't exactly, because they have covalent bonds, and they can't be pulled apart as easily by polar water molecules. Now, what gives minerals their properties? There are two things that give minerals their properties. These are composition and structure. It's hard to read the screen behind me on this tiny camera, but I'm trying my best. Anyway, composition and structure. So, what's in it and how it's put together. Those are the two things that give minerals their physical properties. Composition can affect things like its color, it can affect its bond strength, how strong that mineral is, and structure can affect, again, bond strength, it can affect its hardness, it can affect all sorts of things. So, if we look at what's in it, let's take calcite, for example. If you're looking at calcite, this is calcium carbonate, limestone. If you get that crusty lime buildup, if you have hard water and that crusty lime builds up on your shower head, that's this stuff. It's composed of calcium and carbonate, CaCO3. Now, because it's composed of this stuff, you have various bonds within this material. You have an ionically bonded group you have a covalently bonded group of molecules in your carbon and oxygen, and you have an ionically bonded calcium. So that group of carbonate, that CO3, is approached by the calcium, and that calcium tries to hang out with it. Now, remember, the carbon and oxygen is kind of clicky, doesn't want that calcium to hang on, so it's kind of loosely bonded to those other atoms, which means that molecule can be pretty easily broken. But that doesn't mean that the whole molecule breaks up. So calcium carbonate can be weakly dissolved in water. However, if you put a little acid on it, that calcium carbonate starts fizzing and bubbling, because that acid is enough to break those covalent bonds. That acid will break apart those covalent bonds and completely dissociate that atom or that molecule. So it'll completely dissolve in acid, but it'll only weakly dissolve in water because of its different bonds. So that's how what's in it can affect its physical properties. Now, you can also affect its physical properties by how it's put together. Minerals can have various forms depending on how their molecules are put together. A great example of this is carbon. Carbon is an elemental material. It's only one singular element, but it can be put together in a couple different ways. Now, if you're taking notes right now, then you might be using a pencil, perhaps a lead pencil, perhaps a number 2 pencil. I don't know. Ticonderoga is my favorite brand. Use that. I don't know. Do what you want. But if you're taking notes with a pencil, then you're using some of this stuff. You're using graphite. And graphite is a very weakly bonded material. It's carbon but that carbon forms in sheets. So those sheets of carbon are all held together by a very weak force. We talked about it, we called it the van der Waals force. So those sheets of carbon are held together by a van der Waals force. In those sheets, all those carbon atoms are held together by covalent bonds, but between those sheets, they're all held together by van der Waals forces. Now, you take those sheets of carbon, you put them under huge amounts of pressure, and you heat them up so that they're a little flexible, and you crunch up those sheets into a sturdy framework. Now, all of a sudden, you have a very, very, very strong structure. You have a diamond. So, if you crunch up carbon enough, you can get a diamond. It's the same mineral. What's in it hasn't changed. It's just changed structure. So, what's in it? How it's put together. Composition, structure. Now, if you're following along, obviously this is a little too bright to see, but this is a slide of the silica tetrahedron. Now, the silica tetrahedron is composed, like I said, of a silica surrounded by 4 different oxygen atoms. It forms kind of a pyramid shape. This is a very specific structure. It's a very strong structure. It's a framework structure. And this framework structure actually makes quartz a very hard mineral. But it's not the only structure out there. If you take a bunch of these silica tetrahedron and you link them all up in a chain, you get a chain silicate. If you link them all up in a sheet, you get a sheet silicate. And if you link them all up in a framework, you get a framework silicate. Things like garnet, diamonds, things like that. Well, diamond's a poor example. It's not a silicate, but garnet is a great example. So, how you change their structure and how they're put together can greatly affect physical properties of a mineral. So, next big question. How do minerals form? Well, minerals form in a number of ways. The easiest way is by lowering the temperature below a solidus. Now, you guys might have not heard the term solidus, but I'm sure you've experienced it before. I don't know, if you want to experience this, take a ice cube tray, go to the sink, pour water in the ice cube tray, go to your freezer, put the ice cube tray in the freezer, and let it sit for, 6 hours. After that, pull it out and see what you get. Chances are you probably already know what you're going to get. You're going to get ice. Well, if you think about it, ice is naturally occurring, it can occur naturally, a naturally occurring, inorganic, crystalline, solid, with a fixed or limited range in chemistry. Ice is H2O. So, ice is a really good example of a mineral. And it forms by lowering its temperature to below a solidus, meaning that it becomes solid. It freezes. The same thing happens with lava. The same thing happens with ice. When lava cools, it's just those minerals lowering below their freezing point, which means you start crystallizing things within that lava. So, lowering the temperature below a solidus. Now, the second way you can actually get a mineral is by precipitating it out of a solution. Now, in the ocean, you have a lot of stuff dissolved in there. I'm sure if you've ever tasted seawater, it hasn't tasted great. Word to the wise, don't drink seawater. It's just not good. Fish pee in it. But it does contain a lot of dissolved material. The biggest, the most concentrated material of those dissolved constituents is halite, salt, sodium chloride, whatever you want to call it. And that material is very concentrated in the oceans, about 35 parts per thousand. Now, you also have other things like calcium carbonate dissolved in the oceans. This stuff doesn't dissolve as readily. Now, if you're dissolving something, you have to pull it apart by using all the van der Waals forces of those polar water molecules. So all those polar water molecules are working really hard to pull apart those atoms. If they can't hold them apart, they start going back together. Now, sometimes there just aren't enough water molecules to go around. So if you take a cup of water and you keep dumping salt in it, eventually there's going to be too much salt to dissolve because there's not enough water molecules to pull all those pieces apart. At that point, we've reached what we call saturation. That is a saturated a saturated solution. It can no longer hold any of the dissolved material. This becomes important when you go make rock candy. So, you can try this if you want. I don't know the ratios, you might have to look at that up on the internet, but if you take some water, you boil it, you add energy to it, so those water molecules are all moving around and, bouncing off the walls. You add energy to it, you dump a bunch of sugar in it. That sugar gets pulled apart by all these water molecules. It dissolves. Eventually, it forms this kind of thicker, syrupy type stuff. You pour it into a jar and let it cool. You put a little string down inside that liquid, and you let it cool for like a day or two. Over time, little crystals will start to form on that string. The reason for that is because you've saturated that solution with sugar. And because you've saturated it so much, that sugar doesn't want to be dissolved. There's not enough water to go around. Once that water cools, you've lowered its energy, and it doesn't have enough energy to keep those sugar molecules pulled apart. So once those sugar molecules are not able to be held apart anymore, they start slamming back together, and they form sugar crystals. The same thing happens in the oceans. So, by the way, that's how you make rock candy. If you go to the store, you buy rock candy, that's what you're eating. In the oceans, however, it's the same thing. Calcium carbonate pulled apart by water molecules. Those water molecules can't always hold those calcium carbonate molecules apart, so they slam together and they come out of solution and they form a crystal. And that's how we form some minerals, by precipitating directly out of a solution. Now, the third way is when atoms become mobile. Now, this might not be as apparent to you guys, but atoms can kind of rearrange themselves. If you put them under enough pressure and enough heat, you give them enough energy, they can start to move. A good example of this is what we already talked about, carbon. If you put carbon into a big high pressure temperature, or a high pressure chamber, then it'll squish together, change its shape, and become a diamond. That rearrangement of molecules is what forms a new mineral. So you can get minerals that way too. And the final way that you can get minerals is through biological processes. Now, don't confuse that. That's not to say that these minerals are organic. They're just formed as a result of biological processes. A good example of that would be, snail shells. Snails form shells. These shells are called aragonite. The mineral that forms these shells is called aragonite. It's a very common mineral. It's the same as calcium carbonate, just a different form. And it's formed through biological processes. Snails, mollusks, even squid and octopus, their beaks are formed of this stuff. So that's a mineral that's formed through biological processes. We actually form a mineral. We secrete apatite. And that apatite is located right here. The enamel of your teeth is actually a type of mineral. It's called apatite. We'll talk a little more about it as we go, but that's actually a mineral that we secrete. So those are the four ways that minerals can be produced: through lowering to below its freezing point, precipitating out of a solution, rearranging the atoms, and secreting through biological processes. Now, minerals can be very, very important. There are certain ones that are more common than others, certain ones that are more important than others because they make up so much material on our planet. There are actually about 4,000 species of minerals on our planet today. We tend to only focus on the common ones. Most of the crustal rocks are composed of silica and something else. Now, crustal rocks are composed, and by crustal I mean things on the Earth's crust. They're composed of silica, aluminum, potassium, a lot of these molecules that are kind of, we'll say, lightweight. They're not very dense. And the reason for that is because all the dense minerals kind of sank to the center of the Earth, right? We talked about differentiation of the layers of our planet. So, a lot of these minerals that appear on the surface of our planet are silicates. They contain silica. And there are a lot of groups of silicates. Now, this, once again, can't really see, but I promise you there's a chart back there showing you different types of atoms and their abundance on the surface of our planet. And you might notice that oxygen, silicon, aluminum, those are all atoms that are very common on the surface of our planet. Things that are less common, things like iron, magnesium, nickel, that's all concentrated at the center. So we have all these materials concentrated at the surface of our Earth, and because they're in such abundance at the surface of our Earth, we have a lot of different mineral groups. We have oxides, things that are combined with oxygen. We have silicates, things that are combined with silica. We have sulfides, things that are combined with sulfur. So all these different mineral groups are based on what the root constituent of that mineral is. So if silica is sort of your main root for that mineral, then you get a silicate. It's the same thing with carbonates, with sulfides, oxygen or oxides, things like that. Now, there are different groups and classes of minerals. I'm not going to make you memorize each and every one of them, but it is important to know that you have things like silicates, oxides, halides, things like sodium chloride, and all these different mineral groups that are formed because of the minerals that are abundant on the surface of our planet. Because no two minerals are the same, we have to identify them. And this identification is something that we're going to discuss in part 2.